goes to a rho interact with the nucleus, go to omega, go to phi. So the current of J mu interact with a photon interact with the nucleus can be expressed in this form. And this was known as vector dominance model. The experimental question is, so this is theory. What is the experimental relation? To do this experiment, I moved to MIT and used the same detector, but greatly improved its magnetic strength and detector capability. So the first experiment you ask is rho is a 2 pi resonance. Omega is 3 pi resonance, and therefore they do not interfere with each other. But if rho can go back to a photon, photon goes to the electron-positron pair. Similarly, rho go to omega, omega go to the electron-positron pair. So rho omega will not interfere with pi-pi final state. It should interfere in E plus E minus final state. The experimental difficulty is this branch ratio is 10 to the minus 5. So you need a rejection of 10 to the 8, 1 in 100 million. And this is why it was never found. So in our experiment, the first experiment is we measure rho omega interference, and this is our measured data. Agree with the rho omega interference, does not agree with the rho to electron positron alone. So photon and heavy photon are exactly the same. And then we verify SU3 rules, symmetry rules, and this is the phi to electron positron pair. And the Weinberg's first time rule says the decay of rho, which is the radius, is equal to omega plus phi. Indeed, our experiment confirmed that. A more important thing is forbidden decay of omega to 2 pi. Rho has isotopic spin 1, therefore you have rho plus, rho 0, and rho minus. They go to 2 pi. Omega is only one state, is 3 pi. 2 pi and 3 pi will never interfere. But rho go to 2 pi. Omega can go back to photon. Photon go back to rho and go to 2 pi. And so this must occur. And that time was a very important subject. Does omega go to 2 pi? And there were papers by Nobel Prize winner Glashow and by Jack Steinberger. Nobody ever found this. And we managed to observe forbidden omega to 2 pi decay. By measuring the pi plus, pi minus, if it's only rho alone, will be red color, and the rho omega interference will be the yellow data, which are green with the model. And so the third experiment is the discovery of J particle. We learned that photon and massive photon are almost the same, and they indeed transform into each other. So the question you ask, why only 3 photons? The ore has a mass of 1 GeV. And to go to high mass, we move to high energy accelerator. Let me mention, at that time, quark model was not the most fashionable model. And in fact, I didn't know anything about the quark model. We started doing this experiment by asking a very intuitive question. Why photon, light ray, only go to rho omega phi with a similar mass? Where is the heavy one? So this is our proposal to Brookhaven National Laboratory, which is the best way to search for vector meson is through production experiment of proton-proton collision, go to vector meson to E plus E minus. The reason is vector meson are produced via strong interaction and thus high cross-section. One can use high intensity, high duty cycle attracted beam. Namely, you can take all the beam from the accelerator. EE resonance limits the quantum number to 1 minus, therefore enable us to avoid measurement of angular distribution of decay product. I firmly believe at that time, contrary to popular belief, E plus E minus storage ring is not the best place to look for vector meson. In the E plus E minus storage ring, the energy is well defined. A systematic search for heavy meson requires continuous variation and monitor of energy of two colliding beams. A difficult task requires almost infinite time. Storage ring is best suited to perform detailed studies of vector meson once they are found. So this is the Brookhaven experiment. You have 10 to the 12 proton of 30 GeV on a 10% target. The multiplicity is 10, therefore you produce 10 to the 12, 1,000 billion particles per second. Of the 1,000 billion particles per second, the most rare is electron-positron pair. The ratio is 1 part in 10 to the 8. Therefore, if you want to do a 1% experiment, you need a rejection 1 in 10 billion. 1 in 10 billion is like when during the raining season in Madrid, there are 10 billion raindrops per second. If one of them is red, you have to find that one. So the experiment is not popular at all to the physics community because most of the physicists believe search for heavy mesons was not the most interesting research topic. And few believe such a difficult experiment could carry out. And therefore, the proposal was rejected by most of the leading laboratories in the world. It was finally accepted by Brookhaven National Laboratory. So this is the experimental layout, looking from the top, looking from the side. And so there's a target, 10 to the 12 particles on a spectrometer. There's a M0, M1, M2 are magnets. C0, CE are Cherenkov counters. Capital A, B, C are proportional chambers. Small a, B, C are scintillation counters. And so the Cherenkov counter is used to identify the electron-positron pair. The bending is in the vertical direction, and therefore momentum and angle are measured independently. So M0, M1, M2 are dipole moment. Capital A0, A, B, C are proportional chambers. Small a, B are counters, and CA, C0, CE are gas Cherenkov counters, and S is the shower counters. Then we'll have a way to calibrate the detector. If you want a rejection of 10 to the 10, you must always know where you are, and therefore we have a calibration. A calibration is to put a magnet very, very close to the target, and you measure pi 0 to E plus minus decay. So this follows the same design of the first experiment at DG. With 10 to the 12 particles produced, okay, you need to protect yourself, protect the instrument. So we have 10,000 tons of concrete, 5 tons of uranium, 100 tons of lead, and 5 tons of soap. Soap is to stop slow neutrons. And I never had any problem requesting money from the US government The only problem I had was requesting 5 tons of soap. And finally, MIT decided to buy this for us. It's hard to justify to a government that you need 5 tons of soap. So this is the experiment, and these are the Cherenkov counters, annihilation counters, and the proportional chambers. The first thing to do is the target. Instead of one piece, we'll put many pieces of target, much thinner. A signal for E plus E minus will come from one place. A background will come from 2 places. And this is the arrangement of the target, and this shows the coincidence of E plus E minus, showing the background is small. The magnet. The magnet we measured 100,000 points, 10,000 points, and the detectors are smaller than the magnet, and they are away from the target. And so only charged particle goes through, neutral particle will not enter into the detector. To reject particle of 1 in 10 billion, you do 3 things. First, to reduce the possibility of a pion goes to a Cherenkov radiator and produce an electron. And to do that, to reduce that, you use hydrogen, because it has the smallest number of electrons. And second, you separate the 2 Cherenkov counter by a magnet, because this electron then, which has low energy, will be swept away. The Cherenkov counter has a large spherical mirror with a diameter of 1 meter, and this is followed by another Cherenkov counter. The separation of the 2 counters by strong magnet ensure the minimum number of knock-on electrons produced in the first counter are swept away. All Cherenkov counters are painted black, and so the background doesn't produce additional light. These counters are extremely important, the most important element. And so this is a Cherenkov counter, and it has a large spherical mirror, and 1 meter in diameter, 3 millimeters thick, and very little material, 125 micron mylar, with hydrogen inside. And this was designed by Marcel Vivajean, Jean-Jacques Aubert, and myself. The mirror were made at precision optical shop at CERN. So this is a picture of the mirror, and this is the photomultiplier, and this, you can see the detection of 1 photoelectrons and 2 photoelectrons. Detector calibration with the pure electron. So you let the main proton beam on the target go through. You build a very special magnet with a hole so you can go through. And then in here, you put a Cherenkov counter. So you have a pi 0 go to E plus E minus, and the electron will go to the main detector, and positron will go to the Cherenkov counter. In this way, you have always an electron beam to calibrate your detector. If you don't calibrate, you must assume something could go wrong. These are the Cherenkov counters, and they are measured with many, many points and many combinations to make sure they are close to 100%. And so Jean-Jacques Aubert made major contribution to the success of the experiment. He later on became the Director General of the French funding agency IN2P3. The position detector was designed by the late Professor Ulrich Becker, and since there are 20 megahertz of particle passing through, 20 megahertz is a high number. How do you sort out? And you sort out by remembering in high school geometry, if you have an equilateral triangle, then you have A1 plus A2 plus A3 equal to B1 to B3 plus B2. And so this is one of the chambers. There are total 11 chambers. And this one, after the experiment was over, was exhibited at the Washington's Smithsonian Institute. So there are 10,000 wires working at a very low voltage so you avoid radiation damage. So these are the arrangement of the wires. They're 20 degrees apart. So all three wires for a real signal will add up to be a constant. So this is the Ulrich Becker, who got his PhD degree with me, and later on become professor at MIT. And these are the proportional chambers. In the early summer of '74, we took some data in the high mass region, 4 to 5 GeV. However, analysis data show very few electron-positron pairs. By the end of August, we tuned the magnet to accept low energy for 2.5 to 4 GeV, and immediately we see a peak. Most surprising, most of the pairs are at 3.1 GeV. I took this data from my Nobel lecture. Throughout the years, I've established certain practice in the group with regard to experimental checks on our data and on data analysis. Let me share with you a few examples. First, is to make sure the peak we observed was a real effect and not due to instrumentation bias or readout error of the computer. We took another set of data at a lower magnetic current. This has the effect of moving all particles into different parts of the detector. The fact that the peak remains to be the same as 3.1 GeV with the full length of magnet, full strength of the magnet, or 90% of the magnet, and showing that the discovery is not due to instrumentation because you collect them from different parts of the detector. And so our paper was published in November 12th. November 13th is Professor Richter's group, and November 18th is from Fiscardi. So this member of the group, by the modern standard, is quite small. This is Jean-Jacques Aubert, Professor Min Chen, and this is Susan, my wife. The unique property of the J particle is its lifetime is 10,000 longer than other particles. The significance of this is similar to suddenly you discover in a remote region on Earth, where people live instead of 100 years, but 1 million years. That means something new has happened. And the spectrum, first measured by Daisy, later on measured by Slide, is like an electron-positron atom. And therefore, because of this, people believe it is from quark, anti-quark family. This is the most important thing, that is, you have a long lifetime, and your transition is like an electron-positron pair, meaning something new, unexpected has observed. And so it was announced, physicists find support for charm quark idea, and that was on the New York Times, a long article. I received my first congratulation letter from Richard Feynman. Richard Feynman said, "Congratulations, but why do they give prize to guys who discover things that I don't understand, don't expect?" please do not let price go to your head. And this was a very good advice, and therefore I never sign any petitions. So this is the awarding ceremony of Nobel Prize. This is Richter's daughter, Elizabeth, and this is my two daughters, Jeannie and Amy. Since that time, many electron-positron collider has been built. And there's, in Italy, there's Adoni, and then there's in Daisy, there's Doris, there's in Stanford, there's Spear, and in China, there's BEPC-1, BEPC-2, which has a very high luminosity. It's still going on till 2030 or so. So in total, in China, in Beijing, they have discovered about 30 new particles from decades. Happened. Doesn't move anymore. So let me now share with you electrons at higher energies. And that's the time we had this Spanish group join us for electron-positron collision. This is known as the Mark J experiment. And so the first group of Spanish joined us, led by Juan Antonio Rubio, Marco Serrata, Bernardo Adiva, Javier Verdugo, Carlos Maña, who is still here, Jose Celesio, and two others. Over the years, we have benefited from many discussions with Alvaro de Lujula, and this was our first meeting in Madrid. So the first measurement is measure QED, namely continue to look for the size of the electron to see whether the electron has a measurable size. And we also measure mu plus mu minus angular distribution to see the Z0 effect. And in order to avoid systematic error, this detector, which weighs 1,000 tons, can be rotated in theta and in phi to average out systematic errors. So this is the announcement in Physics Today of American Physics Society of this measurement, showing our measured forward-backward symmetry at 35 GeV does not agree with the quantum electrodynamics prediction of only one photon, but must have a virtual Z0 effect, and indeed our measured data agrees with the electroweak effect. More important was the sudden observation of gluons at petrol. When you have a positron-electron collision, you produce quark, antiquark, and gluons. Now, quark, antiquark, and gluons eventually become jets. Jet has 50% charged particle, 50% neutral particle. So this is with the increase in energy, you see the growth of 3 jets. But to do that, you must measure the total energy. Indeed, if you spread this out, you can see there's 1 jet, 2 jets, 3 jets, the total energy. They agree with gluon emission, does not agree with the other theoretical model. Just observe 3 charged tracks in a plane is necessary, but it's absolutely not sufficient. And this is in Physics Today. And this was there's a long article in New York Times of detection of elusive gluons. And then we had a collaboration continue with the CMR, and that is the 100 GeV positron-electron collision, and this experiment lasted for 20 years. And this indeed is a large international collaboration involving the United States, Soviet Union, China, India, Spain, Germany, France, and so forth. So this experiment has a magnet, weighs 10,000 tons, slightly larger than this building, 6 stories high, come from Soviet Union. This was the largest overseas collaboration from Soviet Union. The muon detector, part of them was done in CMR in collaboration with MIT, and this is a fabrication of precision muon detector, which has a resolution of 17 micron, and this is done in Madrid. Another important thing is the BGO crystal to provide accurate measurement of light rays and electrons. When we proposed the experiment, the world's total production was 3 kilograms per year, 4 kilograms per year. We need 12 tons. So most of people think this cannot be done. And finally, we found an institute in China who found a way to develop 12 tons of crystal in 3 years. And this is one of the crystal. It has a transparent, but has a density of stainless steel. So BGO crystal are now commonly used in industry and in medicine. There are many publications of this paper, of this experiment. Let me list 3 as example. First, so-called coupling constant, which actually changes with energy. The coupling between gluon and quark, known as alpha S, is not a constant. It decreases with the QCD, quantum chromodynamics theory. The alpha, which is known as 1/137, also changes with energy. More important, with the BGO crystal, we can measure E plus, E minus, go to neutrino, gamma ray. But measure the gamma ray distribution, we see they are only in a model-independent way. There are only 3 types of neutrinos. So now, let me share with you what we're doing at this moment. Namely, the electron-positrons at highest energy, the AMS experiment on the space station. Charged cosmic rays have mass, and they are absorbed by 100 kilometers of Earth's atmosphere, which is about 10 meters of water. So the properties, such as the absolute value and the sign of the charge and momentum of charged cosmic ray, cannot be studied on the ground. To measure cosmic ray charge and momentum, you require a magnetic spectrometer in space. And this turned out to be quite difficult. And you can imagine you have a magnetic compass effect. If you put a magnet in space, one end will point to the north, the other end will point to the south. And so you lose control of the space shuttle and space station. But we managed to figure out a way the magnet doesn't change in space. So this was constructed in Europe and Asia, assembled and tested at CERN, ESA, with NASA support. And so there are one layer of detector, another layer of detector, another layer of detector, and the Spanish made major contribution to this detector. And the magnet was designed at MIT and manufactured in China. And then there's the time of flight counters. It's manufactured in China because the best permanent magnet material come from Inner Mongolia, which is still part of China. In 2 years' time, we will add 4 + 4 square meter of silicon detector on the top to increase the acceptance by 300%. So Spanish participation in AMS under leadership of Aguilar, the late Javier Verdugo and Carlos Maña and Jorge Casals, they are making very important contribution, particularly from CMR. So this is the Spanish group at the beginning. They all now look a little bit older. And this is the Spanish group made a major contribution in the design and construction of the ring image Juncker detector, and in particular in physics analysis. And this is a detector which has 11,000 photosensors separate the charge and velocity. So Spanish industry is involved in the electronics, and this is all last fitted during the construction. And this is the visit of the United States Senator Ted Stevens, who was the chairman of the Senate Committee on Science, on Commerce, Science, and Transportation. And, this is Carlos Maña and Javier Verdugo, Manuel Aguilar explained to Senator Stevens. And then also the US Senator Bill Nielsen, now the head of NASA, and this Javier Verdugo explained to him how this experiment. And this is the visit of Christina, Minister of Science and Technology, in Kennedy Space Center before we launch into space. And this is Manuel Aguilar explaining AMS operation to the NASA administrator, Charlie Bolden. This is the head of NASA. So the unique properties of AMS is it's like a magnetic spectrometer. It has a precision and redundant measurement of matter and antimatter. So there are 5 detectors, and the electrons, protons, ion, positron, antiproton, antimatter all leave different traces. And second is continuous momentum scale verification. In space, one thing you have to remember, once you're in there, you cannot go there to check it. And so you better know what's going on all the time. And so we have 4 independent measurements of positron momentum, energy, and electron momentum and energy. So for this spectrometer, the energy minus momentum for positron and electron are the same if there's no bias. From this, we know the momentum to 1/34,000 GeV. That means at 1 trillion electron volt, the uncertainty is less than 3%. This detector is designed like the first electron-positron pair, or like the J-particle experiment. So we have accurate and redundant measurement of E plus E minus with TRD, or positron-proton separation 1 in 10,000, and electromagnetic calorimeter, positron-proton separation 1 in 10,000. And they are separated by a magnet. So E plus minus produced from proton interaction with detector do not enter into ECOL. So the first thing is cosmic electron, positrons, and antiprotons. They have 3 possibilities. One of them is from ordinary cosmic collision, produce energy, produce positrons, antiprotons. If dark matter is a particle form, dark matter collision produce energy, can produce positron, antiproton. Pulsar is a rotating neutron star. It has a strong magnetic field. So light ray interacts with magnetic field, will produce positrons. But it does not produce antiproton because the mass of antiproton. So this is our measurement based on 4.2 million events from very low energy to 1,000 billion electron volts. This is the spectrum. The spectrum, the low energy part, agree with the model for cosmic collision. So the question is, what is this? Why this come about? And this can have only two possibilities. One is from pulsar or from dark matter collision. But if you fit the data with the empirical formula, and then you see your empirical model says this spectrum is equal to a collision part, which is this part, and plus another spectrum, but you must have a cutoff. Namely, the spectrum doesn't go continually up, it must go cut off. And the confidence level is very close to 1. One of the reasons we will go to 2030 with the upgraded detector is this leftover part of the spectrum can be explained by dark matter collision with a mass of 1.5 trillion electron volts. But this agrees with dark matter prediction, but you certainly cannot claim you have seen dark matter because the error is still very big. This is why we want to collect more statistics to make sure you have agreement with dark matter model. Also, you want to see a point out of the production of dark matter collision. Electrons also is unexpected. Electrons from collision are very small. Electrons can be explained by two power laws, Ca E gamma A, and another power law, Cb E gamma B, plus the positron term that you take from the positron spectrum. And this confidence level is 98.8%. By 2030, will be close to 1. So the existence of this means that you do see either a pulsar or dark matter model, because only pulsar and dark matter will produce equal amount of positron and electron. This is a mystery why electron data over a large range can be explained by 4 numbers, Ca, gamma A, Cb, gamma B. Nobody knows why it is like that. The Spanish team, under the leadership of the late Javier Verdugo, have made major contribution to physics analysis. Then we also measured antiprotons. Antiprotons are very, very rare. But we found the spectrum. About 60 GeV, positron and antiproton are almost the same, the spectrum. By 2030, if the trend continues, they will be exactly the same. If they are continue like this, it means the positrons most likely come from dark matter collision because pulsars does not produce p-bars. Spanish leads the analysis of anisotropy. Astrophysics are point sources for impinging a higher astrophysics arrival direction of energetic positron than a small dark matter model. Dark matter will be everywhere, pulsar will have a fixed direction. And this is Jorge Casals, Carlos Manuel, and Velasco. And by 2030, we will separate between pulsar prediction and dark matter prediction at the 99.3 confidence level. This will be a major contribution from CMR. Now, let me share with you something totally unexpected, and that is on cosmic rays. Cosmic rays have two kinds. Primary cosmic ray, proton, helium, carbon, and so forth. They are produced during the lifetime of stars and accelerated from supernova explosion. So they propagate through intermediate before they reach AMS. Measurement of primary cosmic ray are fundamental to the understanding of acceleration, propagation of cosmic ray in the galaxy. What we found, light cosmic ray, helium, carbon, oxygen, has one functional dependence from 60 GeV to 3000 GeV. And neon mechanism silicon have a different dependence. The fact primary cosmic ray have two identical dependencies is not expected, not predicted by any model. And then there are secondary cosmic rays, lithium, beryllium, boron, and fluorine. And they are cosmic rays produced from primary cosmic ray with interstellar media. So measurement of secondary cosmic ray are important understanding propagation of cosmic ray in the galaxy. Secondary cosmic ray also have the same rigidity behavior. Rigidity is momentum per unit charge. You have lithium, beryllium, boron, and they are two order of percent exactly the same. And fluorine is different. This again is totally unexpected. Cosmic rays come in all directions, different energy, different property, but their energy dependence is exactly the same. Not predicted by any model. And then if I look, light nuclei between Z equals to 2 to 8, you have two classes, helium, carbon, oxygen, with a primary cosmic ray, lithium, beryllium, boron, secondary cosmic ray. For Z to 9 to 14, you have neon mechanism silicon in one dependent, fluorine have another dependence. Now, let us look more carefully on the property of cosmic rays. This is the abundance ratio measured by NASA on the surface of the sun. You notice normalized to silicon. Oxygen flux is 5 times more than neon flux. So silicon flux is 2.4 times more than sulfur flux. Ion flux is 17 times more than nickel flux. And therefore, oxygen, silicon, ion are primary cosmic rays. Lithium, beryllium, boron, fluorine, scandium have the lowest yield, and therefore that's pure secondary cosmic rays. Another unexpected result is before MS, taking into account 50 years of tradition, assuming carbon is pure primary and boron is pure secondary. The B over C ratio has been used to modify to describe cosmic propagation. But with the accurate data, we now found carbon actually has a primary part, like oxygen, namely 0.83 times oxygen, and another part, the secondary, 0.7 times boron, across the entire spectrum. That means carbon is not pure primary. The question is, now how do you use this theory? Because the fundamental assumption is not correct. So look more carefully. We found even the nuclei and not the nuclei have distinctly different primary and secondary composition. Even the nuclei like carbon, neon, magnesium, sulfur, primary dominance. And odd the nuclei nitrogen, sodium, aluminum, secondary become permanent. So now all the cosmic nuclei, you can know which is primary, which is secondary to high accuracy. Something totally unexpected cannot be explained by any theoretical models. And so there can be all the cosmic ray, out of the 21, out of the 28, the other 7 will be measured shortly, and they can be decomposed into 2 primary class and 2 secondary class. So finally, the universe is very simple. Charged cosmic ray only has 4 classes. Now let me share with you some information on antimatter. The Big Bang origin of the universe requires matter and antimatter to be equally abundant at the beginning. So the question is, where is antimatter universe? And this was proposed already by Paul Dirac in his Nobel Prize speech in 1930s. Heavy antimatter has never been found because to find it, you need a magnetic spectrometer in space to measure the charge. From 100 million deuteron, and 10 billion protons. This is the bending plane, non-bending plane, production angle. This candidate has a charge -1 plus minus 0.05, mass 1.9 plus minus 0.1, just the opposite of deuterons. Even more interesting is anti-helium. This event has a charge -2 plus minus 0.05, mass 3.81 plus minus 0.29, just the opposite of deuteron has a charge +2. So the discovery of J particle 50 years ago opened up a new realm of physics. Space is the ultimate laboratory. Space provides particles with much higher energy than accelerators. The AMS result requires the development of a new model of cosmos. And I want to mention the Spanish physicists and the industry has made major, fundamentally important contribution to this experiment. Thank you.
Thank you very much, Professor Tim. Since it is getting late, I think that we have time for 1 or 2 questions.
Thank you, Mr. Ting, for your time and your contributions made to the science. And
speak slowly.
Sorry, sorry. Thank you for your time, for your presentation, and your contributions made to the science and for the humanity. This is the result of your personal history of determination and resilience. And I wanted to ask you, how did you deal with the rejection of some of the results of your experiments and the problems derived from them all along your career?
Most of my experiments not accepted by the community. There's always something new, and at least a few experiments none of them are related to the other. But physics does not depend on vote. Public opinion, community opinion, of course, is important, but the more important is to destroy people's opinion. Therefore, you can move ahead. You cannot vote on physics results. And so, normally, if I decide to do an experiment, I mentioned at the beginning, I talked to 2 or 3 physicists. Richard Feynman was one of them, Panofsky was one of them, Robbie was one of them, and another one called Steve Weinberg. I talk to them and listen to their opinion, but I don't do what they say. Okay? I just see what they think. But I never have listened to a theoretical physicist's opinion. Before me, there was Álvaro de Lúcula gave a talk. I have great respect for him. We are very good friends, but I don't listen to what he tells me. Because you really need to believe what you say. Otherwise, you really cannot carry out such an experiment. Yes, there's it.
Well, Mr. Samuel, thank you very much for your presentation. I subscribe what my colleague said before. And, well, basically, I'm very amused and happy to talk with a Nobel Prize. That's first of all. But later, I have always read that antimatter was more abundant than matter. And you have said that there's like a proportion of 50-50, or that's what I understood. So what are you based on?
I give example based on if the universe comes from Big Bang, and before the Big Bang is vacuum. Nothing exists in vacuum. So at the beginning, at the Big Bang, you must have an equal amount of matter and antimatter. Otherwise, you will not have a Big Bang. So that's just a simple example. The most important thing is to find it. If you don't find it, you can have many theories. Yes, there's a lady.
Professor Ting, well, I'm a physicist also. This person that has said that antimatter is more abundant is confusing antimatter with dark matter. And this happens very often, unfortunately. But simply is confused. So this is the problem.
To the best of my knowledge, they have nothing to do with each other.
Of course, have nothing to do with each other. Yeah. But many people confuse antimatter with dark matter. It's a fact. Yeah. I know because I talk, I'm a scientist, particle physicist, and I give talks for outreach. And I talk, well, I have written also a book about antimatter, I can show it to you. So I know that lots of people confuse antimatter with dark matter. Yes. And of course, dark matter is leaks like 3 times more than ordinary matter. I mean, it's the abundance, no? Yes. So it's much more. But antimatter is much, much less than ordinary matter. At the starting of the universe, exactly as you said, it probably was 50 and 50 at the starting of the universe. But nowadays, antimatter is extremely, extremely small proportion. It's extremely small compared to ordinary matter. Huh?
Yes.
It is time to end this magnificent session. So, Professor Professor Ting, thank you very much, and good luck for the future.